Let's talk about the singular value decomposition. The abbreviation is SVD, Singular Value Decomposition. What is the singular value decomposition? Let's take some given matrix A and we want to decompose A. We already decomposed a lot of time. We had the LU decomposition, that means given matrix A, find a lower triangular matrix L and find an upper triangular matrix U such that L times U is the given matrix A. Or the QR decomposition, an orthogonal matrix Q times an upper triangular matrix U equals A. And now we decompose again, but this time we have a product of 3 matrices. That's a little intimidating maybe, but we will see it's not that difficult. Okay, we have an orthogonal matrix U. U is orthogonal as well as V is an orthogonal matrix. And then we have a diagonal matrix S, and then this product is A. In this video we will not talk about how to find this decomposition. We did that in every detail for the LU decomposition or for the QR decomposition, but we will not do so for the SVD. Okay, so we will use a MATLAB command to find this decomposition, and then we will see what we can do with this decomposition. This time we will not solve a system of linear equations, but we will do something else. For example, we will analyze images, or we want to compress images, so we don't need that much memory space. Okay, but let's start with the decomposition, and let's start with a simple example. Please give me, let's say, a 3 by 3 matrix A, whichever you want. Okay, maybe you give me this matrix with these 9 entries. And now let's call MATLAB, or let's call Octave to find this decomposition. So let's enter the matrix A. And now we will get 3 return values. They are normally named U, S, and V. And the command is singular value decomposition of A. And then we get that answer. Let's write that on our paper. Let's use a rounded version of these matrices. So maybe you notice that these 2 entries are equal and these 2 entries are equal and these 2 are also, but that has nothing to do with the principal concept. That is pure coincidence, so forget that structure. What was the diagonal matrix S? It was this one. Okay, what was the matrix V? This is the rounded version of the matrix V. And now we can multiply, we can test if it's really true. We can multiply the matrix U times S times V transposed. And let's see if this equals matrix A. Okay, we multiply U times S times V transposed, and we get the matrix A. How do we multiply? We multiply step by step, so maybe we first multiply S times V transposed. Let's write that to our paper, and then we multiply U times that, and then we get the answer, which is A. So this was the matrix U times S times V transpose, so let's transpose. And then let's multiply these 2. And what does that mean? Here we have a diagonal matrix times a matrix. This matrix will scale that matrix, and it will scale every line. The first line will be scaled by 28, the second line will be scaled by 1.74, and the last line will be divided by 10. And so we get, let's multiply by approximately 30. 30 is 3 times 1.2 and 12. and here by 30, 1.8, so 17 or 18, and here again almost the same. And now let's multiply this line by a little less than 2, so we get 0.28, but a little less than that. And here we get a little less than 1.3, and here we get a little less than 1.4. And here we divide by 10 more or less. And now we can multiply this matrix by that matrix. So to get the first entry, this one is this product plus this product plus this product, and if we do that, then we get this one. We get this 11 by multiplying here times here times here, and we get that 5 by this times that, and we get that 8. This product plus this product plus this product, and so on. And so we get indeed the matrix A. Okay, so we saw a little example. What we did not see is what is that good for. Okay, we will talk about that now. Okay, so let's introduce some writing. Let's write the first column of U as this vector, the second column, and so on. And let's write for the columns of V, V1, V2, and so on. The matrix S is always ordered with entries larger than 0. The largest one is in the position 1, 1. The second largest one is in the position 2, 2. And in our example, the least one was in position 3, 3. And that would be sigma 3. And that is the principle of the decomposition. Possible are also values 0, but that was not the case in our example. And how can we reproduce the matrix A? We can reproduce it by multiplying U times S times V, but as well we can reproduce by this product. This is the first singular value, and then the first column of U times the first column transposed. So that will be a line. Column times line is a matrix, and then this matrix plus that matrix plus that matrix. And instead of expanding to the full length, we can also stop at some point, and then we have an approximation of A, and that we will later use. Okay, I'm sure we need an example to better understand, so let's do that example. Okay, what does that mean here for our example? That means that we can get A also alternatively to this product in the following way. Let's take the first singular value, which is 28 times 1/8, times the first column of U times the first column of V transposed. So this column times this line is a matrix. 3 by 1 times 1 by 3 is 3 by 3. In that case, if we do that multiplication, then we get 0.08 and the minus on top times that line. So this is more or less a tenth of that line. And so we get, and then the second line is this times that is more or less 1. So that is more or less a copy of that line. And in the last line, it's a little less than half that line. So we get these 3 entries, a little less than half, a little less than half, and then plus the second singular value times the second column of U times this column transposed. I don't want to expand that. And then the third part is 0.10 times the third column of V transposed. And if you do all these calculations, then you will also get A. Okay, what can we say about that? The first thing is that due to the fact that U and V is orthogonal, that means that this matrix the elements in this matrix are of a defined size in total. Orthogonal means this vector measured in the Euclidean length, so square that entry, square that entry, square that entry, add them, you will get 1. And here do the same, square, 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 and add these, then result is 1. And here also, that means here this is also length 1, also length 1, also length 1. And if you multiply these two vectors, which are both length 1, that will result in the following fact. Square these entries, these 9, add all these, and you will also get 1. So this matrix is of Euclidean, some kind of Euclidean length of 1. And this factor means how much energy is in that part. So here we get a contribution of weight 28.18. This contribution to A is only 1.74, because here again we will have Euclidean length 1 in total, and this part will contribute only a length of 0.1. This times that, square all the entries of this matrix, add them, and then you will get 1. So Euclidean length of that matrix is 1. This is the first thing I want to say. Then the second thing is that really a surprise that we can reconstruct A like that? And this is not a surprise. If you multiply two matrices, this one and that one, you can always do that multiplication in a very special way. If we have a matrix U, let's say this matrix consists of the following columns: U1 column, U2 column, and U3 column. That means this is U1 vector, U2 vector, U3 vector, and you can take whichever matrix you want. It does not need to be orthogonal, nothing, take every matrix whichever you want. Okay, let's take a matrix, let's say W, and it consists of lines. So this is line W1, line W2, line W3. And if you multiply U times W, then U times W, you can also get the result of this multiplication by taking U1 column times W1 line plus U2 column times W2 line plus U3 column times W3 line. This seems to be a little surprise that this is really true in general, but you can easily prove by introducing the concept of block matrices. But instead of proving, we want to see an example. Let's say A is a random matrix, entries are integers between 0 and 100 or 99, I don't know. Let's say it's 3 by 3. And let's say B is another matrix, also 3 by 3 in our example. And then we can multiply A times B. And instead of doing the multiplication we did here, we can also do A, take the first column of A and multiply with the first row of B. And then you will get a matrix. We see here, now the first row of B. The result is a matrix. And now let's do that plus second column of A times second row of B plus third column of A times third row of B. And then we have to compare with that here, 9176 and so on. But here a little error, but to my surprise I don't get an error message of MATLAB. I don't understand in the moment why we don't get an error. Okay, but let's do it right. Then we get the same as A times B. Okay, all entries are identical. So instead of multiplying in the normal way we know it, we can also do the multiplication here. And so this expansion is not a speciality of the singular value decomposition, but it's more or less a general fact. And if you are not really familiar with that concept, maybe it's helpful to give one example, which I better gave right in the beginning. If you have a column matrix times a row matrix, then the result is take the first line times 1, take the second line to be 2 times this, and take the third line to be the result of 3 times that row. Or alternatively, take 10 times the first column, take 11 times this column, and then is this result, and then take 12 times this column, and you get that. Let's go back to the script. We already talked about that. That means that the Euclidean length, the norm, the Frobenius norm of the matrix A is always 1. So these parts are all of norm 1. These are norm 1 matrices. So the impact of that part is given by the first singular value. The impact of that part is given by that singular value, because this is Frobenius norm 1, as this was also, and so all the impacts of these parts are given by the singular values. And if they decrease as fast as they did in our example, starting with 28 and then 1.74, so we have more than factor 15 between these two, that means that this impact is by factor 15 less than this impact was. And then we have again impact by factor 15, 1.74 compared with 0.1 is more or less also factor 15. So this impact is much, much smaller. And that's what we want to see also. So let's go back to our matrix A we started with. So this was our A, and then we decomposed by using that command. And so we have A, and now let's compare the U, first column of U, times first column of V transposed, and then times the first singular value. And then let's compare that, and you see 1 compared to 1.01, 11 compared to 11.099, and 5 compared to 4.7. 1 compared to 1.49, 16 compared to 16.37, and 8 compared to 7. 2 compared to 1.5, 17 compared to 16.57, and 6 compared to 7.11. So most of the matrix A is explained by this first part of the sum. And the reason for that is that this singular value is much more than this singular value and this singular value added. So most of the contribution comes from this first part. But if we take into the sum also the second part as 2 times, then we are even closer to A. So compare these two, and the matrix A is almost reconstructed. Very slight differences. Why is that so close? Because we have the third singular value to be only 0.12, so or more or less 30 compared to 0.1. So most of the information of A is included in that sum. And if we take the third part, then we are completely identical to A. Okay, that's great. That's really, really great. So what do we have in the script? Here we have also an example which is not 3 by 3 but 3 by 5. If you want to, please read and redo the calculations. Okay, and now a second example, we take an image which is an array of pixels. If it's monochrome, that means if a gray scale image, not red, green, blue with colors, but only gray, then you have an array of pixels. And what are the values of the pixels? The values are for each pixel a number between 0, which means black, and 255. 255 means completely white. And if we have such a picture, this is the picture, the original one, then we have in this case an array of pixels with 480 rows and 640 columns. So that means, it's 307,000 bytes of size. And now we can say, okay, this array, we can also do the singular value decomposition. And if we store not the complete information, but only the first column of u, the first column of v, and the first singular value, then we have a compressed version of the image. It will not be the original image, but something more or less close to the image. Maybe we can also store u2, v2, and sigma 2, and then we get a better approximation of our original picture, and so we can take more summons into that sum, and then let's see what happens. For this picture, if this was the original picture, the first approximation looks like that. So it's not a very good approximation, we can't see any detail, but the rough structure of the picture we can see. Then the second one, the watch, now is quadratic. This is kind of funny. It gets a circle only from step 3 or better on step 4. Very funny is this watch shows a time. It's 5 to 3 o'clock. And here it's a quarter to 3 o'clock. That's really funny. I can't explain that in detail. I don't understand that in detail, but I see that on that picture. If we take one more summand here, then it's also a quarter to 3. And then after 15 steps, we can see an approximation which is quite close to the original picture. And storing these vectors and storing the singular values takes only 17,000 bytes instead of 300,000 bytes. So we get a compressed version if we want to compress using that singular value decomposition. If we store all the u and v vectors, then we also get the image, but then we did not compress, but then we inflated the information, so we need double the information more or less. So that would be not a good idea. Compressing with this technique works best for rectangular structures lying even in the image. So if the image is of that kind here, so this is maybe the picture of the German flag or something like that, then this compressing technique is perfect. And also if it's of that structure, if it's the flag of Belgium, then it's also a very effective strategy to use the SVD decomposition. If you really are interested in compressing images, as far as I know, the SVD decomposition is not a technique which is used in that context. There are better ideas, but this is one of the ideas, and this is one of the ideas you should test, and then you should compare with other ideas. But for me, it's a fascinating example how you can use or maybe use this mathematical tool. And now I want to give you one more example. I coded here some code, and then we get the following. This was the picture I downloaded from the internet, from Pixabay. And if you do the SVD decomposition, you get the following singular values. The first singular value is 30,000. The second singular value is less by factor 4. So the first part explains a lot of the picture. The third singular value is 6000. So the picture is not explained in every detail by the first part, but the rough structure is explained of that picture. That's what we see when seeing these singular values which are ordered. The first one is always the largest one, the second one is the largest of the rest, and so on. This was the original picture, and this is the first part of the picture. So that is the first singular value times the first column of U times the first column of V transposed. And then we get this approximation of our original picture. Here I plotted in red color the first column of U, and in blue color the first column of V. And let's find the link between what we see here and what we see on the original picture. And this is quite fascinating. Going from top to down, what do we see? We see the picture starting with a dark area. Then it gets bright. But here are some lines which are very dark again, and then it gets darker and darker. So we start with 0 values, which means more or less dark. And then here in this bright section, we get these values. And these black lines are the reason for this. Here, instead of being very bright, it falls back by 25% back. Why 25%? Because this width is almost 25% of the total width, and this is almost white, and so this is the explanation. And so we see that structure, what happens in that picture going from line to line. Okay, that's the red. And the blue one is going from the left to the right. Going from the left, it starts with being very, very dark. This part, very, very dark. But then here we get some bright section in the middle of the picture, and then going to the right here we also see that and that. This is this black line and the white line. So it's very fascinating to see the link between this picture and these two vectors, the red one, the first column of U, and the blue one, the values of the blue one, the first column of V. And what can we do now? We can do the same as I did with my picture in the script. I take the original picture, do the SVD decomposition, then multiply the first column of U and the first column of V transposed and take the first singular value. And then I get this approximation to my original picture. And then if I take the second part also into the game, then I get this approximation. Now I'm at step 2. And now I can step 3. We get closer and closer to the original, and 4, 5, 6, 7, 8, 9, and 10. That is kind of fun. I strongly encourage you to try to reprogram, and please do that for any picture of your choice. Then it's a lot of fun to see the link between your picture and this, and to see what's happening when doing the reconstruction. So this is a lot of fun. And as I said, we don't try to understand how MATLAB, how Octave does the decomposition. What is the technique behind that? In my script, here's some mathematical background, and this has to do, at least from the mathematical background here, I can prove that there is always a SVD decomposition and that it's more or less unique. But I don't want to go into these details. These details were important for me being a mathematician, but I don't want that you care if you are an engineer. So we are done with the SVD decomposition, which decomposes a matrix A into a product of U, S, and V, where U and V is an orthogonal matrix and S is a diagonal matrix carrying the singular values.